Hello. Today we will be talking about the neuron story. And to give a brief overview, I'm going to be talking about cell structure, the three neuron network, and the beginning story, neurotransmitter binding, ion exchange, threshold of excitation, generation and propagation of action potential, and saltatory conduction. So to begin, synaptic transmission, or the neuron story, explains in a simplified way how neurons communicate with each other. The neuron story always starts with an event happening, or in other words, a stimulus. The stimulus in this case will be pressure being applied as a result of a physical hit. The three neuron network we are using to illustrate the synaptic transmission is the reflex arc of cell A, the sensory nerve below the knee on the patellar tendon, cell B, the interneuron located in the lumbar region of the spinal cord, and cell C, the motor neuron located in the knee. Cell A, B, and C all differ in morphology and location, but the one thing they all have in common is the fact that they all have a synapse. This means each cell is similar because each have a space between itself and the next cell. The synapse, or synapse region, consists of three parts: the presynaptic membrane, the postsynaptic membrane, and the synaptic cleft, which is the functional space between the two cell membranes. It is important to emphasize that the synaptic cleft is not merely a space, but a functional space, because important work is done within this space. And I will expound upon that in a little bit. Another thing that the cells have in common is that they are all completely surrounded by interstitial fluid, which is located on the outside of the cell. And they're all filled with different fluid called cytoplasm, and that's inside the cell. If we take a closer look at the synaptic region between the presynaptic membrane located on the axon terminal, or the terminal button, of cell A, and the postsynaptic membrane located on the dendrite of cell B, we can see that there are vesicles located within cell A. These vesicles are filled with neurotransmitters, which are being emptied into the synaptic cleft between cell A and cell B. This is why the synaptic cleft is referred to as a functional space. If we were to zoom in even further to the dendritic membrane of cell B, we can see that it is composed of lipids that form a bilayer. Within the postsynaptic membrane lies a receptor which spans the entire bilayer, called an ionotropic receptor. And just as the name denotes, it is a receptor for ions. The ionotropic receptor is typically in a closed configuration. Now, back to the neurotransmitters that released into the synaptic cleft. When these transmitters were released, four things can potentially happen. It can be taken back up into cell A by a process called reuptake. It can dissipate or float away. It can metabolize through a process called enzymatic degradation, or, and this is the possibility we will be focusing on, it can bind to the binding site of the receptor located on the dendrite of cell B. When the transmitter binds to the binding site, it causes the ionotropic receptor to change configuration and open up. And we can see down at the bottom here, on the left side, we have the lipid bilayer, and then we have the receptor that's going all the way through it, and that T there stands for the neurotransmitter. In the first image on the left, it hasn't bound, but then on the right, we see that it has bound, and that receptor is now open. Now, because the receptor is ionotropic, I like to think of it as hungry for ions, and this is where understanding the composition of the interstitial fluid in cytoplasm is a bit more comes into play. Both cytoplasm and interstitial fluid contain many components, but we will be focusing on three specific ions: sodium, chloride, and potassium. and we'll be focusing on their concentrations as well. Interstitial fluid has a high concentration of sodium, a high concentration of chloride, and a low concentration of potassium. Cytoplasm, on the other hand, has a low concentration of sodium, a low concentration of chloride, and a high concentration of potassium. Cytoplasm also contains other charge-producing constituents, but we won't try to identify them. We just consider them all together as an ion, and that contributes to the net negative charge inside the cell. And to better visualize it, here in the right corner of the image, we see that the red line is now the membrane, and then we have the interstitial fluid is blue, and that's the outside of the cell. We have that transmitter in we have the receptor in the middle with the transmitter bound to it that's now open, and on the inside of the cell, which is, we denoted it as orange, is the cytoplasm. Once the transmitter has bound to the binding site on the receptor, a pore on the receptor will open up, and this particular pore is permeable to sodium, so it will allow sodium ions to come into the cell because of two forces acting upon it. These two forces are osmosis and electrostatic pressure. Both of these forces act simultaneously to support the mechanism of the ion pores. Osmosis is the force that is a result of all molecules' desire to be equal across a semi-permeable membrane by moving down the concentration gradient, and electrostatic pressure is the force that results from opposite charged molecules always attracting each other and same charged molecules always repelling one another. In this case, because the sodium concentration is high on the outside and lower inside, osmosis will take effect to promote the balance of sodium across the semi-permeable postsynaptic membrane of cell B. At the same time, electrostatic pressure will be acting upon sodium to enter the cell because opposite charges attract, and as stated before, inside the cell is more negative and sodium is more positive. The only way that this ion movement can be measured and studied is by an oscilloscope with electrodes spanning the bilayer, which can be attributed to Hodgkin and Huxley. Here is a drawing that depicts the ion movement and the activity that corresponds while using an oscilloscope. When the ion pore is closed, because the transmitter has not bound to the binding site on the dendrite of cell B, the outside of the cell is at rest and registers at -70 millivolts. Now, when the pore opens and sodium begins to enter the cell, we see a slight rise and eventually a bump called an EPSP, or excitatory postsynaptic potential. The EPSP registers and denotes the depolarization of the cell. Depolarization means more positive, which makes sense because sodium is entering the cell and making it more positive. However, when there are multiple dendrite receptors being bound to, which is more likely the situation since the body releases several transmitters at a time because there are several cell A's and several cell B's in the body with somas that have thousands of dendrites on them for potential binding. There is a summation of EPSP that add to each other. Summation of EPSP charge happens in the axon hillock of cell B. The summation continues until the threshold of excitation is reached at -65 millivolts, which is the charge necessary to open voltage-gated channels. Once the voltage-gated channels are open, there is an influx of sodium ion, which results in a huge depolarization spike, which you can see there on the chart that I've sketched here. The spike continues until sodium reaches equilibrium at +55 millivolts, and we can see at the top there it says sodium equals sodium. At this point, the potassium ion channel opens and a similar mechanism happens, except now potassium is desiring to go out of the cell because inside the cell is too positive. Remember, because of electrostatic pressure, similar charges repel. Now, potassium wants to move down its concentration gradient to balance out as a result of osmosis. However, as the hyperpolarization As the cell hyperpolarizes, which means becomes more negative, in an attempt to reach equilibrium, it overshoots a bit to negative 75 millivolts, but only briefly. When this happens, the cell brings itself back to rest at 70 millivolts, negative 70 millivolts, with the help of proteins on the cell membrane called the sodium-potassium pump. And we can see that denoted in the image as well. Ultimately, the movement of the ions produce bioelectricity that is conducted in the soma and sums together in the axon hillock and spreads down the axon shaft by traveling from node of Ranvier to node of Ranvier. At each node, you have a sodium-gated channel and a potassium-gated channel that are opened by the action potential. The action potential would start at the axon hillock, run to completion, then return to rest, as depicted in the oscilloscope drawing. Then it would go on to the first node, run to completion, and return to rest. This will happen at each node of Ranvier. Eventually, the action potential would reach the terminal button of cell B, where it interacts with calcium ions so that the vesicles bind to the presynaptic membrane of cell B, resulting in exocytosis, where the molecules of neurotransmitters are emptied out into the synaptic cleft between cell B and cell C. The process of the action potential traveling down the axon shaft is called saltatory conduction. And that is the neuron story.